So here I am back to the same equation. Dinitrogen plus 3 hydrogen molecules gives us 2 ammonia molecules plus heat. Back in 1918, a German chemist by the name of Fritz Haber won the Nobel Prize for getting this reaction to go forward. But if we think back to the last slide, we had just mentioned that delta G was a negative 33 kilojoules for that reaction. Well, if that's the case, then this reaction is a spontaneous reaction. So how does someone win a Nobel Prize for getting a spontaneous reaction to go forward? So what Fritz Haber had done was he looked at Le Chatelier's principle. Le Chatelier's principle said that if you add heat to this reaction, then the reaction should go back in the reverse direction, right? So in terms of temperature, he knew that he wanted to keep the temperature as low as possible in order to drive the reaction to the right. He also looked at pressure, and you ought to be able to take a minute here to think about this in terms of would a high pressure or low pressure work. So put me on pause for a bit and come back. And when we take a look at this reaction, we see 4 gas molecules as reactants, 2 gas molecules as products. So if you put a really high pressure on this, you might squeeze those 4 molecules together and cause them to make 2 molecules, thereby relieving that stress that you're putting on it. So Haber was looking for a high pressure, low temperature system in order to get this reaction to go forward. The other thing that he did was to add a catalyst. The catalyst that he added was essentially rust. So not a very expensive catalyst, but one that caused this reaction to go forward a little bit faster. All right. So why is it that we need to do these things at all when it's a spontaneous reaction? So if I look at an energy diagram for this reaction, what we find is that the nitrogen and hydrogen start off as reactants with a reasonable energy, and the products are down here at a slightly lower energy. And so we have to get from reactants to products. In order to do that, you have to add a lot of energy in order to break that nitrogen-nitrogen triple bond. That's a very difficult bond to break. That activation energy is enormous. And so that's part of the reason for the high pressure. The low temperature is going to help drive the reaction to the right, but it turns out that he ended up using about 450 degrees Celsius in order to get this reaction to go forward. That doesn't seem like a very low temperature to me, but the reason for doing that, of course, was to get the reaction so that its kinetics were somewhat suitable. In other words, if you keep the temperature low, you get a high percent yield, but it just takes a really long time in order for that to happen. So you add enough heat in order to get these things moving forward, and then you sacrifice your yield. So the yield is only about 30%, but it turns out the products are easy to separate from the reactants. So the temperature doesn't kill you there. Turns out that we use about 200 atmospheres of pressure for this reaction. If you use 1,000 atmospheres of pressure, that works a whole lot better. The problem with using 1,000 atmospheres of pressure, if you could imagine putting that kind of pressure inside a container that has nuts and bolts in it, those bolts are going to go flying across the room and kill somebody. So you always want to have a low pressure if possible, just from a safety point of view. Why is this reaction so important? Why the Nobel Prize for doing it? And the answer is sort of twofold. The reason that Haber did this reaction in the first place was because the Americans and their allies had cut off the supply chain of saltpeter, ammonium nitrate, to Germany. They had been using ammonium nitrate as their explosive, right? So ammonium, that's supposed to be a 4, nitrate. Right? You'll notice that there are 2 different nitrogen atoms in this molecule, and those 2 different atoms, nitrogen, can combine together in this nitrogen gas as a stable molecule with a triple bond. So they had been cut off from their starting materials to make explosives, and so that's why he needed to do this reaction. Doing this reaction, by the way, is what we call fixing nitrogen. Plants can fix nitrogen, or at least some plants can. Those kinds of plants that will do that are plants like soybeans, or actually any bean. Those are in a group called legumes. Legumes have these little nodules on their roots that contain bacteria in them, and those bacteria can take atmospheric nitrogen and break it down to make amino acids, and then from amino acids they can make proteins. So it was very important for the purposes of making molecules for explosives, but ultimately this reaction has been useful because it now feeds the world. Ammonium nitrate is an excellent fertilizer, and so that's why the importance was necessary, or the importance was needed to get this reaction to go forward.